Yes, one of those. It may or may not have sound. Find out later. And then I guess we do want to share the screen. Probably. It makes more sense to see. Well, actually, later on, we're going to do some weird stuff. So, how do we? Yeah, just share this screen. Okay. Well, that just confuses me. Let's just share PowerPoint. Share screen, PowerPoint, share. Are we still recording? Yes, I think that's what, yeah, recording on this computer. Okay, great, hopefully this works. Okay, let's see how we do. Okay, this looks good. This looks good. So today we have our class, lots of stuff going on. We'll get to that in a moment. But next week will be office hours in here. If you have questions as you work on your new assignment. Thursday after that, your papers will do. So this module is a paper, a little different from the first paper because you're going to be doing a whole research report. So with an intro and results discussion. We'll come back to that at the end of today. And you'll submit it on Blackboard just like before. And then the Thursday after that, spring vacation. And then when we come back from spring vacation, we'll start our fourth module on the flanker effects. So different experimental effects we're going to talk about today. Questions about the schedule? Great. So today, let's see. Maybe over. Where's the least obtrusive spot? Down here. Kind of 5 sections of today's class. We'll actually talk about group results from last week. Then we'll talk about stimulus response compatibility, kind of all the cognitive psychology theory behind it, also human factors research. We'll talk about testing ourselves on a new experiment. This experiment is slightly different, but the protocol is very similar. You know, go to the lab, use MATLAB. I think we'll take a quick trip to the lab, but it should just reinforce what you did last module. The data analysis will be more complicated or involve more steps this module. So after we go to the lab, we'll come back and say, okay, how do we process these data in Excel? And then our last section of today will be about how to craft the product, the paper that I'd like everyone to write either as an individual or groups. That still applies. So Hick-Hyman group results. So this is reaction time mean. And a lot of people saw very nice strong linear relationships in their data. And these are the grand means. So if you imagine each of you have a mean for your performance in simple reaction time, and then we average all those means together. So it's a mean of means. So sometimes we call that a grand mean. So that's what these values are. You know, it's got a great linear fit to it. And then this is the range of the correlation coefficients. So R, to get R squared, you just square the R value. But on average, it was 0.97. It ranged from 0.95 to 0.99. So very strong linear relationships to mean, which I think matches what we saw. The other thing that was noted was standard deviation of reaction time, you know, didn't have a great linear fit. The grand means, it actually looks okay here, but that's because everyone was quite different. And when you average all that together, it usually looks somewhat decent. But if you look up here, I think the best story is shown by the range of R values. So not nearly as high. There's quite a range to them. So yeah, the Hick-Hyman law seems to occur for reaction time mean, but I don't think this is a strong enough linear relationship to say that we're seeing the Hick-Hyman law for reaction time standard deviation. Any questions about the group data? For this module, again, you'll be analyzing your own data. One reason for that is we're going to look at the compatibility effect. and everyone should see that in their own data. Sometimes in cognitive psychology, we look at things that you really don't see until you average, 10, 20, 100 people results together. But we're trying to stick to things that we see at the individual level. That also makes data analysis a little bit easier. So, you just have to analyze your own data. You don't have to then do that for your 10 peers. And that also makes your presentations and papers a little more unique because you'll have your own personal set of data. Stimulus response compatibility. So what is stimulus response compatibility? I think the easiest definition is it's the degree of naturalness between a stimulus and a response. And when we did hit Hyman law, it was very natural, say in two choice, that the left stimulus requires a left response. The right stimulus requires a right response. That has a very natural association. And left going with left, right going with right is probably something that we're born with, that has evolved within our nervous systems. But we'll also look at other stimuli and responses that we're not going to be born thinking that a sign that says H means hospital up ahead or an H on the ground means helicopter. But those things we learn over the course of exposure and experience. So stimulus response compatibility can encapsulate both of those things. Natural tendencies, that we're born with, or things that we learn through exposure. So why is this important? We're going to look at it from two different angles. And first, kind of the fun, applied side, maybe a little less theoretically driven, is how compatibility is applied to human factors and ergonomics. So human factors is the design and engineering of human machine systems for the purpose of enhancing human performance. This is a kind of a relatively recent field that really took off post-World War II. And what they saw, Professor Paul Fitz, was one of the early practitioners in this area. He served in World War II, and what he saw is that the design of the machines contributed to, accidents, which would sometimes revolve in people losing their lives. So, and he looked more specifically at aviation safety. And before his time, if engineers got together to build an airplane, he said, okay, well, we got the airplane, we need some controls. What's the easiest way to physically make these controls? And that's good because it's easy to build, but sometimes it was bad because what's easy to build is not necessarily easy for the human. And Paul Fitz kind of led in this era of human factors, which continues to today, and I would see no sign of stopping, of, well, how can we make interfaces intuitive for humans, the ultimate end user? This is a big field. Areas, maybe the biggest areas where you could get a job would be the automaker industry. They put a lot of time into, one, it could be luxurious end. So how do we make this very intuitive, comfortable interface? But there's also, of course, matters of safety involved. Aviation, military. Within the military, you have people interacting with interfaces, whether that's a computer screen or a rifle, all sorts of human machine interactions. And these are often by highly stressed, highly fatigued soldiers. And there you want things to be as compatible, as obvious, as perfect as possible, because it's very easy for accidents to happen. And then computers. So, it could be website design, but it could also be, for example, how Apple invests more into the operating system interface, keyboard, their simple remotes. They put a lot of money into that because they want these intuitive interfaces that are appealing for individuals. And one is so that people pick that product over another. So we'll spend the first half of this section talking about kind of fun examples of human factors. Then we're going to get back to cognitive psychology and say, well, what from compatibility can we learn about the way the brain works? Maybe more specifically, what is occurring during response selection? So question one on the test, compatibility. When something is incompatible or compatible, what we're changing is the duration of response selection. Is it easy or is it hard? We have a whole group at Texas Tech and at many universities that focus on human factors. Here at Tech, they're within the psychological sciences department. And some of their research would be more applied, but I mean, you can also be very, basic science approach to factors. A few examples, every time I come into class, I have my USB drive and I need to plug it in. And the one thing I don't like about this adapter or interface is that it's one way. You can only go in this way and it can't go the other way. And it seems like, well, it probably wouldn't be too hard to design it so that it would be plugged in either way. It's like USB-C, right? And is lightning bidirectional? Can you do it either way? Yeah. So that's great, right? And I mean, I'm probably not going to lose my life, and class probably won't be too late if I plug the drive in wrong. But this is just a simple example that would make an everyday interaction easier. QWERTY keyboard. So, like we all use a keyboard where the layout is referred to as QWERTY because it spells QWERTY in the top left here. Has anyone heard about how they came to this layout? Oh, don't spoil the surprise. So there's a few different ways that this story is told. So whether or not this is 100% accurate, but it goes something along the lines of the origin of typing was with mechanical typewriters. So you may have seen an electronic typewriter before. We got to think even earlier when it was mechanical typewriter. What would happen? You'd press a key, and an arm would come up, kind of almost like a piano, and it would hit an ink ribbon, and on the key would be the letter, and that behind would be your paper, and it would leave the impression of that letter on your paper. So it was a mechanical device. And that was fine at first, because no one had typed in this way before, so everyone was quite slow at it, as you can imagine. But some people, that was their job, 8 hours a day, or 12 hours a day, before labor laws existed. You would do this a lot, and some people got very good at it. And the problem with mechanical keyboards is typewriters, is if you press two keys too quickly, the arms will jam together because they're both hitting the exact same spot. So then, you got to get in there and unjam them. You maybe ruin the paper, you got to start over. So it was a problem. And the mechanical typewriter company said, okay, well, what can we do about this? And instead of making a better mechanical keyboard, they said, what if we arrange the keys in a way that is inefficient for typing? So that has led us to QWERTY. So some numbers about QWERTY here. So this is the home row where your fingers rest. Only 32% of your typing is in the home row. So most of the time you have to travel to get a key, and that takes time. That's inefficient. There's also a slight bias that you type a little more with your left hand than your right hand, which is probably good for lefties but bad for righties. It's maybe not the worst possible arrangement, but it's definitely not the best. Do we have better layouts? Yeah, and one of them is Dvorak. Sadly, the keyboard doesn't spell Dvorak, but that was I guess the inventor's probably last name. And here, 80% of your typing is in the home row, and you can see, like the vowels, which you use a lot, are right there in the home row. Although I'm kind of surprised they're not under your right hand, for example. But there is a slight bias in Dvorak that slightly more typing is done with your right hand than your left, which is best for the majority of the population. Why have we not switched to this? Well, they've estimated that the cost to switch is larger than the cost to stay with QWERTY. If we switch, we'd be really bad at typing for a while, right? It's like some countries there where they've changed, forget which one, but they have done this where they say, okay, midnight, New Year, everyone, we're now going to drive on the right side of the road instead of the left, or vice versa. And it's happened, it's just crazy for the first one. Same thing would happen if we all suddenly our keyboards got replaced, we're using Dvorak, we would all be slow. And it would take a while, we'd be slower, and then as we relearn or retrain ourselves, we eventually would be faster. They've estimated that the cost of switching doesn't outweigh the loss of the initial decrease of performance. There could also be other issues. One thought is what they could say is, okay, everyone born starting this year in school will learn Dvorak. Then eventually, QWERTY would die out with, say, all of us. But we're not. There's no plans to switch. I did, when I was in engineering, I did have a few friends who used a Dvorak keyboard. And this isn't actually the most efficient. They still kind of tweak and do some research on that. Is that similar to what you had heard about it?
I learned about it in your undergrad class.
Oh, yeah.
So
It's probably the same, okay. My apologies for using some examples twice.
Just reinforce.
Here's a street sign that is obviously, gonna be too complicated, right? You're driving, it's fast, you're in a killing machine, as I like to refer to cars. And all of a sudden you gotta figure out what's going on here. And I always thought this was a ridiculous sign until I moved to Texas. And something for those of y'all from outside of Texas, these Texas turnaround lanes, which I've heard some students call them, I have never seen those before. So does anyone know if they're mostly in Texas? Like if we go to Louisiana or New Mexico, do they have those?
They're not in New Mexico.
They're not in New Mexico?
I drove from Chicago to here and did not see that until I got here.
So maybe they really are a Texas turnaround lane. I think they're great, but the first time you see them, you're like, what? Like turning, U-turn? So this I am now familiar with these signs, and it's not a big deal. You can imagine someone new to Texas, or maybe even new to driving in North America. They're used to driving on the other side of the road. They throw in this complexity, and that can cause an accident. All right, we're gonna go one more example, and I have we'll do a vote. So we could talk about poorly designed doors. I think for each one of these I have a little video too. Or we could talk about the 2000 presidential election. Just
I already know what I'm voting for.
oh, you haven't seen 3 yet. Oh, I guess it's on your slides. And then number 3, roundabouts. So who would like number 1? You of course can watch the video at home. The 2000 presidential election. Trump was not involved. Okay, we got. We got.
I kind of want to see where it's going.
You want to see that? Okay. And then everyone left was roundabouts. I'm excited the election one because in the undergrad class, since I've started this one, it's always been roundabouts. So, why?
It's so random. It's right there.
That's the animal sciences one. That's the closest one I
think there are 2 total.
There's like
one
that.
there and it's the one.
Oh
over
yeah,
by
the hotel, right? Overton. Yeah, actually. So here we'll skip this. Yeah. So for round.
Oh, there's also neighborhood. Yeah, you know which neighborhood? Yeah.
Well,
Your
the one
neighborhood.
that's behind.
Yeah.
It's over on like 15th Street, right?
I'm thinking, hold on. How many can we find?
So there's a third I need to go check in. All right, let's talk about the 2000 presidential election. So how old were y'all in 2000? 5.
Like /0.
I'm trying to think, do I? I don't know. I lived in Canada, so we probably heard about it on the news, but I wasn't intimately following it. So it was George Bush Senior, George W. Bush versus Al Gore. Sorry? George. Oh, is his father? W.
I was George W. Or is it?
Oh yeah, sorry, not senior, it'd be George Bush. The younger Bush.
Yeah.
Has I'm assuming his father is probably passed away. So I think Bush was running for re-election. I think this would be his second term, no, first term? First term, okay. Al Gore, and so ultimately George Bush won the election, but it was very close. Let's see. So we probably don't need the video here. Let's just look at the most controversial state, which was Florida, and it did come down to whoever won Florida was going to win. So in the end, Bush won Florida by about 2,000 votes. The controversy was that there was 10,000 overvotes, and overvotes were when someone punched, so you had to punch one hole in the voting card. An overvote was when you punch more than one. So did 10,000 people go in and being like, screw this? Probably not. So these are likely individuals that got confused and made a mistake. And we're going to see that the way they voted, the ballot box design was not very compatible. It was easy to get confused, especially in Florida, where everyone is at least 80 years old. That's what I've been told. So within these overvotes, we'll look at them in a moment, but I'm going to suggest that maybe about 1.6 were for Bush, 5.3 were probably for Gore, and 2.9 were also probably for Gore. So if you say, okay, Bush won by this much, we'll give him that many more, but then we got to give Gore all of these votes. That would actually swing the election in favor of Gore. And if he had won Florida, then he would have won the presidency. So what did the vote look like? And they've tried to digitize and improve a lot of these voting machines, especially after issues with the 2000 presidential election, although now there's a lot of controversy over security of digital voting, because then it could be potentially hacked, I mean, these you'd have to physically get in there and mess with them. Whereas the digital ones, there's always a concern anyone around the world could get into machines. I'm not suggesting that happens. It just is a concern. All right, so the way this would work is, let's say you wanted to vote for George Bush, you should vote Republican, and here it would show you, okay, Bush or George W. Bush is running for president, and Dick Cheney would be the vice president. You can kind of see what's happening here is that there are these two names, but you should only punch one hole. So this is a paper underneath here where you're punching a hole in, presumably so they could take those papers and then be counted electronically with some machine that detects where the holes are. If you wanted to vote Democrat, for Gore and Lieberman, president, vice president, then you should punch just one hole here. What happened is, so about 1.6 of the votes, individuals punched both of these holes. Who are they probably trying to vote for? I would think they're probably trying to vote Republican. Maybe they're trying to vote reform and they saw two names, so they thought, okay, I need to vote for president and vice president. But in general, most votes are really for our, the two leading parties. So yes, some people vote for these other parties, but I'm not sure the statistics, but I would think less than 1%. So we're going to say these votes are probably were intended for Bush. Now about 5,000 people punched these two holes, so probably Democratic, but maybe Reform, maybe Socialist, but who really votes Reform or Socialist? And then finally, there were a lot of people who punched these two holes, which probably Democratic, maybe Socialist, maybe Libertarian, but probably intended to be Democratic. But we can't count those votes. There are clear rules. If your ballot has more than one punched hole, then it can't be counted. And if there are any more physical voting out there, that rule still applies. We can't just guess. Has anyone voted with a ballot like this before? Either. So yeah, you can see an issue of stimulus response compatibility, which, I'm sure hundreds of thousands of people voted in Florida, and this wasn't an issue for the majority of individuals, but because the election was so close, it was potentially a deciding factor. Hopefully you're happy you voted for the 2000 presidential election. Okay. So that was just kind of a quick aside into the world of human factors. Lots of more great and fun examples there, but we're gonna get into kind of the more meat and potatoes of this course, which is of course cognitive psychology, and what can we learn about response selection by studying compatibility. So we are going to look at the easiest task I think there is to study compatibility, and it's really just two-choice reaction time, which you're already familiar with from our last module. And when we did two choice, we really did this mapping, which they call ipsilateral. So ipsi, same side, the idea here, same side. Stimulus on the left requires a left response, stimulus on the right requires a right response. Well, from the reading and even without, you can probably see where we're going. We're gonna also do a contralateral mapping. This is what we'll do in the lab at this point. So here it's still two choice, but now a left stimulus goes with the right. So contra, opposite lateral side. So there's an opposite mapping between the stimulus and the response. And left going with right, left going with left, right going with right. We're going to be faster here. Our reaction time will be longer here. And this is probably something innate and inborn, that left goes with left and right goes with right. That's just how spatial information works in the world. I'm not sure how young you could test this, but they've been probably looked at things even in infants, and then you have to rely on, say, eye movements instead of hand movements. And why is contralateral harder? The idea here is that response selection takes longer. Even though it's, this isn't astronomically hard, this isn't as hard as, a physics exam or something, but there's extra processing here. Your brain says, oh, left stimulus, and you naturally want to make a left response. You have to kind of say, oh, don't do that. The instructions are do the opposite. And that small amount of processing will increase your reaction time, perhaps by 100 milliseconds. We'll see what our group data looks like soon. So if we go back to our information processing model with our kind of three major stages. So two choice reaction time between the go signal and the movement beginning. We go through all three stages or 5 substages. And for ipsilateral, which we'll call the compatible mapping, you'll have a short reaction time. When it's contralateral or incompatible, reaction time is longer. And just like in Hickheim, we're suggesting that's because response selection takes longer. Stimulus identification doesn't really change. Your brain's saying, oh, left, right, it's equally good at detecting those things. And then, pressing left or right, pretty equally good at that as well. So when we see a change in reaction time, we are assuming it's to the duration of response selection. Any questions about the tasks so far? Well, I thought we could give it a quick try in class. So I think there's 5 trials, and we'll do ipsilateral first. So you make a left or a right response to a left or right stimulus. And try to think about how hard the task is, how long your reaction time is, and then we'll try contralateral, and you'll probably feel that it's long. Okay, here we go. It's pretty straightforward, right? Let's try contralateral, so opposites. See how long this is. Okay, great. Did the latter feel like reaction time was longer? So when we get you into the lab and we measure it very precisely, we should see that the difference between them, I think, is usually about 100 milliseconds, and that's long enough that you can feel the difference. If something is, say, 10 milliseconds longer than something else, even though we could see that in the lab and with statistics, that's not long enough for us to feel the difference. But I think through the course, we're going to try to stick with things where we can feel the difference. Actually, the last time I taught, we did one experiment where you can't really feel the difference, and I decided to get rid of it. It's just not as fun for individual testing. So what happens when stimuli and responses are compatible? Well, as we've talked about, reaction time is shorter. But we also see there are fewer errors. And we'll actually measure the number of incorrect responses we make in the task this week. And then maybe more relevant for human factors of product design, but we see learning is quicker and user satisfaction is higher. And those things, well, I guess all four of those things are in great marketing tools. Or safety tools as well. But we'll really focus on these first two. That's what we're gonna, those will be the dependent variables we extract from our data. So how can we explain compatibility? And the textbook kind of talked about this in a few ways, and it talked about how, it's not because of anatomy, it's not about the left side of your brain controlling your right hand. But it did give a great model to explain this. And so far we've just said, response selection is longer. But here we're going to look at the dual process model, which explains more precisely why we think incompatible responses take longer. The good news is it's based on information processing. So, we've seen this. The dual part of the model means we're going to see some parallel processing. It's going to look a little complicated, but I think applying it is fairly straightforward. So hold on to your seats. Here's the model. A lot of boxes. And here's the parallel processing. So encoding stimuli is kind of like maybe stimulus detection. And then right from there, two different parts of the mind start processing the same information independently. And then they make a decision about what response they want to make. So here's response selection for the automatic process. Here's response selection for the intentional process. They meet up, they say, hey, do we want to do the same thing? And if they do, then they can just go ahead and initiate the response. And we have relatively few boxes here, so we're going to have a shorter reaction time. And if they don't want to do the same thing, they say, oh, well, we've got some conflict that we need to resolve. It takes a few more steps, and that's going to increase reaction time. Let's look at this in terms of ipsilateral and contralateral mapping. So I think it's much easier to follow that way. So here, participants doing ipsilateral two choice, and on this specific trial, it's a left stimulus, and because it's ipsilateral, that requires a left response. So what happens? Well, we start with some stimulus detection. We say, oh, we see something on the left, and from there, we've got these two pathways that are both going to process that information in parallel and independently. So the automatic process, why is it automatic? It wants to do the most natural compatible thing based on that stimulus. So when a stimulus appears on the left, the most natural compatible thing is to make a left response, because left goes with left. So the automatic pathway says, oh, I saw something on the left. Well, I'm going to make a left response. That's the most automatic, obvious thing to do. So if I want to make a left response, this is response selection, I now need to program a left response. So we're going to prepare that motor command. Then it's going to say, okay, well, intentional process, do you also want to make a left response? So let's look at our intentional process. So at the same time as the automatic process is going, the intentional process says, hey, I need to think more deeply about the instructions. I'm going to spend some time identifying what is actually being shown here and what the instructions are. Okay, so I see something on the left. What was I told? What are the instructions? It's ipsilateral, so I should make a left response. So the intentional process, you can think of this as the part of your brain that remembers and understands the instructions. It says, okay, I was told ipsilateral, left goes with left. So I spent some time thinking about what I want to do. I'm going to select a left response. Now let's meet up. Hey, automatic wants to select left, so I'm trying to show that with the purple arrow. Intentional, dash green arrow here, also wants to do left. Great, we want to do the same thing. So let's go ahead, and the automatic process already actually programmed that response, so we can just go ahead and initiate it. So with the dual process model, when we have a compatible response, we see this short pathway through. They both want to do the same thing, and they go ahead and they do it. Any questions about that one? With the contralateral mapping, it's going to be the same up to this point, where they're going to disagree and have to resolve their conflict. So now let's imagine contralateral, so you're told When it's on the left, you should make a right response. The automatic pathway is the same as the last trial. It says something's on the left, I want to press left. That's just the most intuitive thing to do. So it says, I want to make a left response, and I'm going to program that left response. Intentional pathway says, well, wait a second, I was told to respond contralaterally. So I'm going to go ahead and select the right response. They meet up. Do we want to do the same thing? No. Uh-oh. Who should we trust? We're going to trust the part of our mind that thought more deeply about the instructions. That, kind of makes sense. So if you imagine you had two friends, one knows all about art history, one knows all about physics, and you want to know the answer to an art history question, and they disagree, you're probably going to trust your art history friend. So we're going to trust our intentional process because it's thinking more deeply about the instructions of the task. Okay, we don't want to do the same thing. Well, we got a problem. We already programmed a left response, and we don't want to do that, so we have to get rid of this program. So we abort the left response. We say, okay, get rid of that motor command. We don't need it. We are going to have to program the right response. So here's response programming of the right response. And then once it's programmed, we can initiate it. So 2 extra steps, giving us a longer reaction time. So a lot of boxes at first, but not that much complicated than the information processing which we already know. So if we go back to summarize, maybe I probably should have gone with the opposite side here. But for this ipsilateral mapping, if there's a stimulus on the left, what is the automatic response? Left, right? And what is the intentional response? Left, good. So what is reaction time? Is it short or long? Right. So you're already mastering the dual process model. Contralateral mapping, this is the trial here. So you should be making a right response. Oh, I gave away the intentional. So automatic is left, intentional would be right, and because they differ, we're going to have a long reaction time. The dual process model, it has utility and use beyond just ipsilateral, contralateral mappings. It works in many situations that involve compatible, incompatible, or even congruent, incongruent stimuli. There's a bit of a distinction in that in psychology. But another example is the Simon effect. There was one example of this in the paper where the word is, so wearing headphones and you'll hear the word left or right, and it could be in your left or right ear. That's, I'm trying to remember if that's the earliest version of the Simon effect, and this is maybe the more commonly used one. And then there's the Stroop effect, and maybe you've seen this one before. This is kind of a fun demonstration where you try to read these words. Sorry, not the words, you're trying to read the color that the word is printed in. And here it's easy because the name of the word, which is red, and the color it's printed in red are the same. So the automatic and intentional pathways both say, oh, I want to say red, great, just say red. This is fairly easy too because there isn't a word to distract you, we're just focusing on the color. But then over here, there's this conflict. Now the automatic pathway wants to read the word. And we're not born with the ability to read, but we practice it so much that our brain gets excited when it sees text. It's almost like, I can read it like me. I want to say blue. It's like, well, wait a second, the instructions are to say what color it's printed in. So the automatic pathway wants to read blue, but the instructions are to say the color it's printed in, which is green. And this one's kind of fun to try in class because you are way slower at doing this task. So any questions on our theory? Let me introduce the experiment. We'll take a quick trip to the lab, and then we'll come back and talk about processing the data. So I have kind of gone through the same order or the same kind of method that I showed for our last experiment, and that might help when you go to write the paper. I tried to break it up into sort of the same subdivisions you would see in a manuscript. So yeah, again, we're just really going for conceptual replication of the stimulus response compatibility effect. And conceptual means that it's not exactly the same, but we're actually pretty close here to exactly the same. I mean, it's probably a different monitor and a different keyboard than other labs, but does that matter? Probably not. Whereas the original Hyman experiments, they had the circle of lights where they did 10,000 trials of practice. We didn't do that. So I was humming and hawing about, I guess it's still maybe a conceptual replication or maybe just a replication. So for your method, it's either 1 or 2 participants, depending on whether you decide to do the assignment individually or in a group. Design, what will we do? Well, it's kind of straightforward. We have 2 blocks. We'll do an ipsilateral block and you'll do a contralateral block. And we'll counterbalance that order, meaning participants, I think 1, 3, 5. So odd number of participants, I think, do compatible, then incompatible, ipsilateral, contralateral, synonymous in this case. And then even number of participants, 2, 4, 6, 8, will do contralateral first and then ipsilateral second. So there could be some order effects in your individual data. Hopefully in the group data, any of those things are kind of averaged out by counterbalancing. So what are order effects? Well, maybe in your second block, you're slower because you're bored. You did the first block, which is going to be about 100 trials, so that second block, you're bored and you're slow. Or vice versa, maybe in your second block, you're faster because you're well practiced at the task. I guess either of those could happen, or for different individuals. But by counterbalancing these things, hopefully across the class, they average out. Each block, there's going to be actually 16 practice trials followed by 100 test trials. So the blocks are a little bit longer here than what we did with Hyman, but the good news is there's only 2 blocks. There's actually fewer trials overall. And I did do the randomization so that half the trials will be a left response and half the right response. So mappings, same kind of equipment as before. This is pretty similar to 2 choice because it kind of is a 2 choice task. So on the screen, you'll see these boxes. You'll get a fixation. That's your warning signal. One of them will illuminate. And then if it were an ipsilateral block, you should respond with the J key. I don't know why in the last study I said the variable form here is 1.5 to 2.5 seconds. That was my mistake. It was actually just 1 to 2. So I just highlighted that here to remember. We'll be measuring our reaction. For data analysis, what I would like to see in your papers is a report of mean reaction time, and we'll look at exactly how to do this after we visit the lab. Standard deviation of reaction time, so we've seen those before, and then I guess the new one would be the proportion of the correct responses. In the last experiment, you may have pressed the wrong key a few times. We could have potentially analyzed it there, but what we typically see with incompatible or contralateral mapping is that there will be more errors than the ipsilateral. We're going to kind of make these 2x2 tables in Excel. We'll talk about those later. So for your results, you can take those 3 dependent variables and make 3 graphs. We'll look at examples of how to set up those graphs. Okay, so let's go to the lab. Oh, are there any questions? When are we done?
So whenever we're doing the contralateral, when it's opposite, can we actually like cross our hands, or do they need to stay?
Yeah, let's not cross hands. But as you saw in the paper, that was a whole nother manipulation they tried, right?
Yeah.
And with crossed hands, you'll still see you're faster ipsilaterally than contralaterally, but there was an overall cost. So if there's that graph, this was like normal hand placement, then crossed hands, you still see ipsilateral is faster than contralateral, but overall you're slower because you kind of added in a little confusion. There's actually a study where they gave them drumsticks, and then crossed their hands and then crossed the drumsticks. And they just show again, you still see ipsilateral is faster, but again, it raises the overall complexity. So yes, do normal hand placement. If you want to try crossed hands, you can just do it as like an extra participant number. So, I think the class is participants 1 to 12. If you want to try crossed hands, just write in, hey, 13, me trying crossed hands. Shall we head to the lab? This won't be too long because it's pretty similar to the last. Oh, make sure the door is locked when everyone's out. You want to leave any of your people? You're right.
That's crazy. I mean, kicked my meeting, but.
Meeting?
It just, I feel wild with that.
Last time, do you remember what I said?
My shoes on six. Or was, you took it up?
Yeah.
You should do.
Yeah. Hello, Mia. We're back from the lab tour.
I did it in college. I think I right then. But you know, I'll
Try not to kick me again.
Oh, my bag, like, got an iPad in there. My dog might be in here, who knows?
She's pretty good.
Who did we lose?
My bag. Alex, with my bread.
Within the slides, the next few are just kind of reminders of things we did in the lab. So there's, you know, the full directory to the file, the variables that we're going to be changing. And then there's a picture of the text, sorry, the code went a little hard to see, but I've highlighted. You know, you change your participant num and block num. But you did this last module, so this is probably excessive. That's it. Site toolbox might give this error. Did anyone see this one last time? Oh, that's good. It has mostly good days. I never really know when it's going to act up. And then this is the path to the files. All right, how are we going to analyze the data? How are we going to extract our values? And has anyone taken biomechanics, undergraduate or graduate? This won't be as crazy. Biomechanics always wins for like largest Excel files. There are quite a few steps, but what we're gonna do is we're gonna go through this together, you know, in Excel right now, and this will just serve as kind of a reminder later of the order. But a lot of these are straightforward. Yes.
So I know you're recording this, so if we forget this, is this going just to Mia or like will you upload it
Yeah.
so we can see it?
Hopefully the video has audio, and I'll put it on YouTube, and I'll put the link on our Blackboard page. All right, so what's in this, the slides here are just kind of some of the reminders to back up how we'll go through this kind of together right now in Excel. Okay, let's see. Need to make sure that I'm sharing the right window here from. Why? Okay. Let's see. Share. Just share. I think if I just share the screen, hopefully that will follow along. All right, let's look at some data, and what we'll do is we'll look at the data I collected. So first of all, if you try to open up these files, the CSV files, just by double clicking them here, unfortunately Excel doesn't open them properly, and I'll show you what that looks like. You can see, okay, there's some values, but it's not in different cells. And Excel used to be better at this. If you open data like this, it would pop up an import wizard and say, hey, it looks like you're trying to open a CSV. I don't know why they got rid of that working naturally, but we can kick that process off by, let's see. Oh, this is kind of in the way here. Can I move this? Oh, I can. Okay. So if you go to Data tab, you can then pick Get Data. And one of these is probably the one we want, but it's, I always forget which logo means which. So we can just say, hey, we want data from a file, and it's going to be, you know, the CSV file. So say, okay, and then it's going to say, well, where's the file? And we're going to just navigate to it. Hopefully it will let us do this. Okay, so let's see. I guess this is on my drive here. And so we'll open. So one was the ipsilateral mapping. So we'll open this. Say import, and now it kicks off the import wizard, which used to run just on its own, and it says, "Hey, you've got some data here," and we're just going to say, "Yep, that's fine." You know, if we had weird files, you can kind of specify certain things. But we're going to say, "Yeah, go ahead and let's load that data," and it's going to generate kind of a table with some pretty formatting. Now I don't know why, but it gives us this empty column here, so I'm just going to delete that. And now we have what we're basically looking at is each row is a trial. So this was my first trial. And this is the participant number, so participant 10. This is the block number 1, ipsilateral. This is the trial number 1. This is the original trial number, and that is used when recycling trials, and we'll see that a little later. This is the 4 period, so it's going to be a random number in seconds between 1 and 2. And then what we have here are which side was the stimulus on. 1 means left, 2 means right. So on this trial, the stimulus was on the right, sorry, left. And then this says, hey, what response are we expecting, or what's a correct response? 1 means left, 2 means right. So it's ipsilateral. So if the stimulus is on the right, left, we should have a left response. Over here, this is, okay, is it a practice trial or a test trial? The first 16 trials are practice, and then the rest are test. This column is what did they actually press? Did they press left or right? 1 left, 2 right. So they pressed left. And by comparing these, we know that they made a correct response, because they were supposed to press left, and that's what they did press. This is reaction time. And then here, this final says, is this a bad trial? Is this something we need to recycle? And when it's a 0, it's not a bad trial, it's a good trial. So let's see here. Over here in the PowerPoint, it lists the columns. And what I'm going to actually do is I'm going to, normally I would just type those all in, but I don't want to bore you with that. So let's see. In this file, I think we have, I just typed in, all the column names, so it's easier to kind of look at and say, okay, what is this? What are these data? The other thing, in a separate sheet, God, this is, sorry, my window here is tiny. We got all the things. Let's see, let's open this, let's close this. Don't save. Okay, so we just have this open here. Down here at the bottom, so it's a little hard to see, but we've got one sheet with all the ipsilateral trials. We've got one with the contralateral mapping. Okay, so we go to our steps here. We imported our data. I did add some headers. You don't have to, but it can help because you're like, what are all these 1s and 0s? What we want to do now is get rid of practice trials because they're just practice. That's you warming up. We're not going to count them in the data. So we're just going to delete them. I'm just going to disappear for a while. Okay. So let's see. The first, oh boy. Oh, you know what? Oh boy. Have I already done any processing here? I've already done some processing. Okay. What we want, will it let us do this? So we're going to copy this. Yes. So we want the most raw form of the data, which hasn't been processed at all. So I'm going to open that data again. Oh, this thing is right in the way all the time.
Okay, I don't want any problems.
Oh, no.
No, actually, much today. Like the first time. It's crazy.
Oh, no, we don't want self files.
It's like the first day I had at the school from 8 a.m. to 6 p.m. It's such a lot.
Is that because people are at the conference right now?
No, it's because I decided to not go to the lab today,
Oh, that works too.
which
All right, we've got our raw data
so like
with
that at the beginning of the semester.
headers on here to make it a little easier to read.
I no longer have time to do the prep. So I get home and start doing more work.
So we want to get rid of practice trials. Over here, we can see the first 16 are all practice trials. And what we can just do is highlight those trials. And we're going to delete them. And they're gone. So practice trials gone. Next up, oh my Lord. Okay, we want to sort our trials because eventually we want to know which ones are left stimulus, left response, right stimulus, right response, because we want to calculate an average for each of those and a standard deviation for each of those. So we want to sort by stimulus location, target location, and by whether it's a good or bad trial, because we're going to first look for bad trials to find out how many incorrect responses we made. So to sort data, you don't want to use any of these because that will just sort the single column. And we need to preserve the integrity of the rows. You know, all this data needs to stay together. We can't just sort this, then it won't match up with all the other trial data. So we're going to go into sort here. And we don't want to use these. We don't want to use these. We say, hey, we kind of want a more complicated sort. And it's going to say, okay, I'm going to sort the rows together. And the first thing we want to sort by is the stimulus location. But we want 3 levels to this sort, so we can add another one in here. We also want to sort by target location. And then we're also going to sort by whether it's a good or bad trial. Smallest to largest is fine, either way. So we say, okay, and now what's happened, if we look over here, so this was, well, so we now go trial 17, 18, 19, 20, and then we skip 21 because that was probably a different type of trial. So it's rearranged these rows. And first what we want to do is we want to look at the number of bad trials for a left stimulus and left response. So we have, you know, left stimulus, left response. We're going to see, were there any incorrect responses, any bad trials? And no, see, these are all 0. We're not seeing any 1s. So I didn't make any mistakes. You may or may not, but here I didn't make any. Okay, do we have any bad trials when it's a right stimulus, right response? We're going to look for 1s in here. No. Okay, so when we talk about the proportion of bad trials, this is the kind of table we're going to make. So far, we have 0 incorrect responses.
So if there were incorrect responses, do we need to like just count how many there are?
Yeah, you'll count them, and then there's a division, but in the next block there will be some. So I'll show you that. So these are we're going to want to make a table like this for each dependent variable. So if we're talking about proportion of incorrect responses. Responses. So proportions are different than percent. Proportion ranges from 0 to 1. But if you multiply 100, that would give you the percent. So 0 to 100%. Let's see, we've got a left response, a right response of a left stimulus, right stimulus. We want to complete this 2 by 2 table. Okay, left stimulus, well that was, so left stimulus is 1, right stimulus is 2, left response is 1, right response is 2. So for a left stimulus, left response, that's compatible and ipsilateral mapping, you know, we didn't see any incorrect responses, so we can put in a 0. The other compatible mapping is right stimulus, right response, which is here. So this 2 by 2 is a little weird because these are your compatible trials and these are your incompatible trials. We'll come back and look at the contralateral block in a moment. Well, let's look at our steps here. Okay. So we kind of skip this because we have 0 here, but we'll look at it for the next. Now, if there were any recycled trials, we can get rid of them because we know how many we made incorrect presses for. Now we just want to measure reaction time, mean, and standard deviation for all the correct non-recycled trials. So we don't need to do this step because we didn't have any, but we do need to calculate mean reaction time and standard deviation of reaction time separately for left stimulus, left response, and right stimulus, right response. So if we go back to our Excel file, when this is 1 and 1, that's a left stimulus, left response. So we want to calculate the mean for left stimulus, left response of all of these trials, stopping right there. And I guess you can do this different ways, but what I usually do is just calculate it here over to the side. So in Excel, the mean is calculated with the function average, a little confusing. And we want it to be all these trials. So we're just going to highlight those and give it that selection. It says, okay, there's your mean reaction time. And just to keep it simple, I'll write 314. 314. To get our standard deviation, we just use a slightly different formula. In Excel, it's STD, standard deviation, EV. A lot of programs, it's just STD. Always have to remember that in Excel, you add the EV on there. And we want the same kind of set of trials. It says, okay, your standard deviation is, we'll just round it to 30.4. When you make your graphs, you can use the exact numbers. I'm just simplifying it in this table. Does that seem okay? Cutting means. So then you would do that again for your right stimulus, right response. So I'm going to go, so that's where it will start. And our last relevant trial is there. So I'll just maybe calculate it to the side here. There's different ways, I guess you could do this, but this will work. And has anyone used pivot tables in Excel? Yes, okay. If you want to use those, that's like, it's like the super powerful way to deal with lots of data. So imagine, instead of just analyzing yourself, you had to do 100 participants. You don't want to do this by hand. You can use the magic of pivot tables. Another option, of course, is to get into programming like MATLAB or LabVIEW. Anton, did you do that for biomechanics?
No, for my job.
Ah, cool.
Way back in the day.
So we now have our means here. So we'll say 320 or 330 and 26.9. So these will be three different tables. I'm just putting it all together. And then each table you'll then turn into a graph. We'll look at that second. So those are the steps, although it was a little bit easier because we didn't have any incorrect responses. So let's look at the contralateral block where I do remember I did make some responses. Okay, let's see. We want, nope, we want data. We're gonna get it from the file. So Disma 10 is me, block 2, contralateral. We'll import this. It always has, I don't know if there's something I could do in MATLAB so it doesn't have an empty column, but get rid of it there. Let's see. I won't worry about the headers. We want to get rid of practice trials, which are the first 16. So this is the column. When I do experiments in MATLAB, they almost always have this kind of format, so I'm very used to the numbers, but feel free to add headers to help yourself. So we need to get rid of these trials. Delete. Okay, great. Here, let's go back to the steps. So we deleted practice trials. We now need to sort our data. So we're going to sort. Oh yeah, see, this is where it's nice to have headers because now it just calls everything, columns. So we're going to want 7, 8, and 12. Yeah, this would be much easier with headers, right? Okay, so here we have a left stimulus, and what should you make? You should make a right response because it's contralateral. 0 means it's a good trial, so let's find the bad ones, if there are any. Okay, so it looks like I made one bad trial. Now, if we look at the numbers, I was supposed to make a right response, and this 1 means I made a left response. So that's an incorrect response. There are other reasons you could have a bad trial. The code, if your reaction time is longer than 1,000 or shorter than 100, we'll call that a bad trial. So if you have any of those, don't count those as a proportion of incorrect responses because those are other types of bad trials. So when you find your recycled trials, you gotta check, whether those were from incorrect responses or reaction time being too fast or too slow. Okay, we've got one trial. To turn this into a proportion, we're gonna need to divide that by the total number of trials, of left stimulus right response trials. And there were, let's see if we can highlight it to find out. There were 51. So we want to divide that by 51. For a percent, we would multiply it by 100. We want proportions, so we just don't multiply it by 100. So what is 1 divided by 51? It's probably gonna be a small number, right? 1 divided by 51. So we'll say 0.0.
0.02, do it round.
0.02? Okay. We're going with 1. And again, you can use the actual number in your cell. I'm just simplifying the board. Okay, so the other one we need to look at is right stimulus, left response. So those trials start here. And we're gonna look for any ones that have a 1. Oh, okay, we've got 2. So it doesn't look like reaction time is too fast or too slow, but you were supposed to make a left response and you made a right response. Yeah, so we've got 2 bad trials. And this, how many were there? It should be 52 if everything's working properly. Let's see. Yep, 52 trials. So here it's just going to be 2. All right. 2 divided by 52. And Anton, how are we going to round this one?
0.04.
Good. Enjoy your consistency.
Would you prefer us to put that whole number in our cells?
Yeah, so within
No rounding at all?
Yeah, within Excel, use that exact number. So here, let's open this up here. So here, let me zoom in on this. Here's my little table for the proportion of incorrect responses. And you can see what I've done is I put in the 65. I think I must have forgotten to eliminate practice trials there. See, this was 1 divided by 51, and this was 1 divided by 52. So you can see it is also rounding it here, but it actually has that exact value. And if we say, okay, what is it? It'll say, well, it's that value is in there precisely. And then, so my reaction time means are in here, and I might have messed these up. So it looks like maybe I forgot to get rid of practice trials. Are they the same? 314, 330. Okay, maybe I did that part right. And was it 304 and 26.9? Yeah. But again, those exact values are in here. So if you look at right here, that's the exact value, and then here it's just being rounded 1 decimal place. Okay, does that seem all right, the processing? So now we need to make 3 graphs. And thankfully it's kind of the same graph, 3 times with different data. Let's see, so tried to add a few reminders about, where to find this. I guess this might be a slightly different version of Excel, but we did the get data option. Or maybe it was just a higher resolution window, so it added in the labels. Those are the columns. We need to do it like a fancy sort function. We need to sort on 3 levels. And this is kind of the 2 by 2 that we're building for each dependent variable. Okay, the plot, this is what we want it to look like. And the good news is once we have the 2 by 2 table set up, it's kind of already in the right format for Excel. So I think we can actually highlight all the data like this, and we're gonna ask for a line graph. Insert. There we go. And ta-da! That's our data. Now let's just move this to a new chart. Oops. chart, new sheet. So we can see this a little easier. That is the same as this other graph I showed you, but obviously this one is, being formatted so it's clear and easier to read. And we can try that here. So let's see. One thing, this graph, well, the text is way too small, but it starts at 0, so there's all this white space. We could probably start the graph from 300 instead. Well, let's tackle the text problem first, because that's gonna drive me nuts. So we're gonna make this nice. And on my screen, it probably looks too big, but once you get to PowerPoint, it helps to have it nice and large. So let's get rid of all that white space. That axis. Let's try starting at 300. That looks pretty good. I don't need this many labels here. I usually like to keep to 6 or fewer. So if we maybe go up by 40s, there you go. So that's looking cleaner already. Chart title. Well, maybe don't need a title, but we should have a label on our y-axis. So let's see here, chart design. We're gonna add, and this I think was our reaction time mean. Okay, let's do this. Reaction time mean, the units are milliseconds. That's looking a lot better. This is a little thin, maybe, if I were to be picky about it. No, that's not going to do it. We want to, what is going on here? Sure. Bring on the viruses. Chart design, format. Where is my, everything's so squished because of the low resolution. But I think if we say, well, yeah, so I do it. So we want to edit the line, and let's maybe make it bigger. 5, that should be pretty good. So we can tweak this so that it's nice quality. I guess I was just formatting this for PowerPoint, but we'll be doing papers, so you don't necessarily have to do it quite as striking. But the same principles apply, and really simplify and make it easy to look at. You don't want tiny text. You don't want 100 labels on your x-axis. Now let's go back to look at this in PowerPoint. So that's probably the same thing we came up with. I guess I moved my legend over here, but 6 of one, half dozen of the other. When you see this plot, it's maybe not immediately intuitive what we're looking at. And this is, I think, where it helps to add labels. So you could write on which of these conditions are ipsilateral and which ones are contralateral. That helps. And you can choose to do this or not in your own data. What I often like to do to make it even easier is put on pictures to show what is that condition. So here, left response, that means you're responding with your left hand. So both of these, it's the left hand made a response. And then blue means that it's a left stimulus. So that, when you look at this, as soon as you see that, you're like, oh, that's ipsilateral, right? And then I should say right, it's left response. Then over here, when we look at this picture, it's immediately obvious that's the contralateral condition. And what we're seeing here is what we predict, that ipsilateral responses should have a shorter reaction time than contralateral responses. And that's why we call ipsilateral compatible and contralateral incompatible. Any questions about the graphs? So line graphs, hopefully not too crazy. There should be 3. 1 for reaction time mean, 1 for reaction time standard deviation, and 1 for proportion of errors. The terminology we often use when interpreting the graphs is asking whether there's a compatibility effect. And a compatibility effect just basically means that the data are as expected, or specifically, that ipsilateral is shorter than contralateral. We're not running stats, we're just kind of doing a visual examination. My difference was, can't tell it there. Let's see, how many milliseconds do we have here? Let's see, 3. About 100 milliseconds. You probably likely see something in the same range. Will we see something this perfect for proportion of errors? Yeah, some people might. I think overall we will, but the proportion of errors might not look, this as pretty as reaction time mean. Reaction time standard deviation, I'm also a little unsure. It might be kind of like what we saw with Hyman law, where some people see this and others don't. We'll just have to see. We don't have time here. Is it 6:30? Is it past?
It's
No,
5:30.
You should have been like, yes, it's 6:30. We gotta go.
I don't know what you guys are doing.
Do we want to take a 4-minute break before we talk about the paper? No? Okay, let's go, okay. So last section for today, and maybe the most important because it's all about the product you'll deliver. The good news is we've seen most of it already. So yes, this paper will be different than the first. It's not just the literature, and here I don't expect a long literature review because the paper should only be about 2,000 words. So there should be an introduction. You should refer to some compatibility research that can come from the reading, that can come from class. And if you want, you can also find more to pull in, but you don't have to. There isn't that. The paper isn't that long. So within the paper, what I'm looking for is about a 2,000 word paper, and longer is okay. As the first assignment, some are longer, and that was fine. Some people got excited about the material. Obviously, I like that. But shorter, I always see as problematic because you're probably missing, things that I'm looking for. So we see one of this. Okay, so these are the sections for the paper. So we'll go with the student title page like before. Introduction, but we'll now be adding method, results, discussion, and references. And you did all these in your presentation, so this isn't completely new. It's just in a different format. One thing about the tense, the intro, method, results, they should all be past tense. So we did this experiment, we collected these data. In the discussion, it's more present tense, or more specifically, it's present tense when you're talking about the current experiment. So now the idea is you would say these data show or these data suggest in the present tense. If you in the discussion, let's say you introduce you found a study, you want to talk about it, then you would talk about that study, in the past tense. So they ran that study. But much of the discussion, when you're coming to conclusions, is in the present tense. There's our title page. We've seen this before. I put it here so we have it all in one place, so you don't have to run to the different PowerPoint slides. We've seen this before. I found a slightly better digital graphic, so it's maybe a little clearer here. And this is still great advice for your intro. The method, so this is the APA JARS, or Journal Article Reporting Standards. When they talk about the method and results, it's like all sorts of stuff that doesn't apply to us. So I didn't bother including it. We saw this before for your presentation. I just added in this, and you did this in your presentation, but just to remind you, when you get to the paper and you're talking about what happens on an individual trial, just use a picture, You should have a little text to support it, but don't use just text, because that would be crazy. So if you're like, oh, there's a square with a fixation and a square, a picture's worth 1,000 words, much easier to understand. I don't think you need a picture for the design, that's just ipsilateral and contralateral. You don't need a picture for the apparatus, we know what a computer and a keyboard looks like, but a picture for the procedure is very helpful. Results, we've talked about this before, but I'll be looking for these 3 figures, and there should be a little bit of text to discuss the visual pattern of the figure. So it's say whether, hey, here's the figure, and look, ipsilateral is faster than contralateral. Something, just a few sentences is fine for each figure. Okay, we all on board so far? Okay, nothing too crazy. Discussion. Oh, where is it? Oh, yeah, sorry, this is highlighted. It's not very easy to see here. I did show you this before. I found a cleaner graphic, but I actually stopped it kind of at this point. And I thought it might be helpful to see these. you don't necessarily have to do all of this. There's a lot of things in here, and some are maybe less applicable. So when they talk about threats to statistical validity, well, we're not doing any statistics, so that's not as relevant. But I thought it might help to see the idea of how you might interpret your data, the idea that you should then, generalize, and then you can do some implications. In a 2,000 word paper, like I don't think you could really hit on all of these, but if you want to see which ones of those works for your paper and just your preference. References, we've seen this before. A lot of this was very well done on your first paper. Oh, two new things. Figures, there's an APA format for figures. And if you want to go on a website where they show this in better image quality and with instructions, I've given the link. But basically, for your figure, you start with the figure number, and your first figure is figure 1, your second is figure 2, and so on. And that text is in bold. Then you have a title for your figure. So here it uses title cases where most words are capitalized and it's italicized. And then you have your figure, and they've got advice about, hey, don't forget your X label. But if you format it like we did in class, that'll be fine. You can put notes on the body of your figures. This probably won't be necessary in this case, but of course, there's an APA way to do that. So mostly just figure, number, bolded, title, italicized, and then your nice pretty format below that. You don't have to do a table, but if it's helpful, you can. And there's a format for tables. So it starts the same way as figures, which is nice. Table, the number, and tables have their own numbering as figures. So you have, say, figure 1, figure 2, and then table 1, then figure 3, and table 2. So they have separate numbering. Italicized title, great. And then the one kind of thing that makes it look APA or kind of scientific is notice that there's no vertical lines. That's just, I don't know if other formatting standards do that, but that's an APA thing. And even, the data doesn't have any lines, but any sort of headings or subheadings or totals do have horizontal lines. All right, let's talk a bit about style, being concise, and grammar. So just 3 slides of this world of how I picked apart your language on the last paper, right? So here are some helpful suggestions. Significant is a special word, that we use in research relating to statistics. So you could use this if you're referring to a paper where they ran tests and they found a significant difference. We're just going to be looking at visual differences. So don't say, hey, ipsilateral was significantly shorter, because we're not testing that. Unless you do, and then you can use this preserved word. In non-science, this isn't a special reserved word, but in science it is. This one, I in today's class, I probably violated this a few times, but time actually can't be fast or slow, unless we think about, traveling at very fast speeds where time does slow down or speed up. But a millisecond, is always a millisecond. So when we talk about differences in reaction time, we should always be using, short or long as a comparison, not, faster or slower. You'll definitely see this misused in the literature, but we can do better than that, right? Than everyone else. The other one, this is, I don't know, it's just popular nowadays to not put spaces between the number and its units. But there should be for most measurement units. There are exceptions like degrees or feet and inches. Although you shouldn't be using feet and inches in APA because it should all be international units. But milliseconds, definitely there should be a space. Are we okay with these ones? I want to give a few examples of being concise, which is one of the cores of scientific writing. And these are from your papers, and I apologize and tried not to make it too obvious who they were from. Next year I'll probably use these and then it won't be as individual, but So look, a few examples here. So from these results, they concluded that, that's fine, but we can say the same thing with fewer words. They concluded that. And whenever we can say the same thing with fewer words, we want to do that. Maybe not in poetry or in your English class, but in science, we do. Which could benefit their long-term health as they age. Well, we could just say which could benefit their long-term health. And if we're talking about long-term health, we're implying age. Just simplifying it. 3 different blood alcohol concentrations. Well, we could just say 3 blood alcohol concentrations. If they weren't different, we would probably just say 2 blood alcohol concentrations. So we've got a redundant word in there. This study set out to investigate. This finding could suggest, there's a terminology for this, I think it's called excessive hedges. And it's, okay, you're saying suggest, we like to do that in science, we don't ever like to say, hey, I proved it, done. We often say it suggests, but here we're kind of double suggesting, if you will, and we don't need to do that, we can just say, this finding suggests. Endorsing the results of prior empirical studies through the decades, or see where I'm going with this one, we just say endorsing the results of empirical studies. This, I guess this does maybe add a little more because you'd be like, oh, well, we're talking about 1 year, 100 years. So maybe there could be a situation where you would need to be more specific, but that's probably. 2 grammar things, which versus that, and so I had to go and look up the exact definition, which doesn't really help me, but there's a little rule here that which, like a sandwich bag, can be thrown away. Hopefully it's a paper bag. Well, I guess how much recycling. So here's an example. So these pants, which no longer fit me, should be given away. And if we get rid of this, the sentence still works. These pants should be given away. So which is adding something additional that's not necessary. And I don't mean to mean it's redundant or we should cut it out and be concise. But that's when you should use which. That would not be appropriate here. The other thing with which, often there's a comma before which. That typically doesn't have a comma, although there's lots of cases where it would or would not. Here's an example of that. Do you remember the name of the book that Claire recommended to us? So if we drop, that is referring to Claire. Do you remember the name of the book recommended to us? I guess that's kind of a sentence. But that is a defining clause here. We need it. So we want to use that. We don't want to use. And the other one, I think actually you guys are being really good about this. It's just so common in pop culture and YouTube, and it drives me nuts. Use versus utilize. They're not synonymous. This definition doesn't help me very much when thinking about it. But use, you should use when you're using something in its intended manner. So I use my pen to write in a book. And because pens are made to write in books, you say use, not utilize. Utilize is not the scientific version of use, it's reserved for when you're using something in a novel, unintended way. So I utilize my pen to pop a balloon. A pen is for writing, that's a novel way to use it, so there you could say all right, well that's my diatribe, spelling and grammar and such. I am not perfect about these things, and I'm always working on them myself, but I just think it helps to be a little more conscious and thoughtful and really improve the writing, especially in a scientific context where the format is more controlled. All right, if you have any questions, feel free to stick around. I'll be here next Thursday. If you have questions before or after that, just let me know. We can meet in person, online, in office, whatever. And good luck with your storybook.
I used utilize so much in mine, I just know this.
It's one of those things, like I don't. Also, like faculty meetings.
Yeah, it
So
just
much.
sounds smart.